Now let us derive the array factor. As we discussed before, the far radiation field of a single element is written in this form. Here, the function f of theta and phi depends on the current distribution, and it represents the directional dependence of a single element. The distance dependence appears only in the factor e to the minus jkr divided by 4 pi r. In the case of an array antenna, the field radiated from one element is just the field of a single element. We now want to find how the directivity changes when many such elements are combined. First, let us consider a general n-element array. Suppose that the ith element is located at the position r sub I. Its excitation amplitude is c sub I, and its excitation phase is alpha sub I, where I runs from 1 to n. Then the current of that element is obtained by multiplying the original current by c sub I, and also by the phase factor exponential of j alpha sub I. Therefore, the radiation field of the ith element is given in this form. Also, because the element is not located at the origin but at the position r sub I, the field is obtained by shifting the single element field to the position r sub I. However, the size of the array antenna is small compared with the observation distance r. So, just as in the derivation of the far radiation field, we use the far field approximation. The amplitude can be approximated by 1 over r, and in the phase we keep the first order correction. Then the field of the ith element takes this form. Now let us consider the whole array antenna. The total radiation field is simply the sum of the fields from all elements. In general, the values of c sub I, alpha sub I, and r sub I are different for each element. Formally, we can write the sum in this way. If you look at this expression, the quantity that depends on I appears only in this summation part. So we collect that part together and factor out the remaining factors that are common to all elements. Let us define the collected summation in this form. Then the radiation field of the entire array antenna is written in this form. Here, the expression consists of the factor depending on the distance, the directivity of a single element, and this new factor. This factor is called the array factor. The former two factors are exactly the same as the radiation field from a single element. So, the radiation from array antennas is the product of the radiation from a single element with the array factor. How do we construct the array factor? It is determined by three things: the positions of the elements, r sub I, the excitation amplitudes, c sub I, and the excitation phases, alpha sub I. By changing these quantities, we can create many different forms of f. In other words, starting from the directivity of a single element, we control the overall directivity of the array antenna by adjusting this factor f. That is why the question becomes how to configure the array factor.